Rotational dynamics problem type 1, falling and rotating. This is the small radius and it's 0.05 meters, and the bigger radius is 0.15 meters, and the mass of the yo-yo is 0.15 kilograms. And since this is only in the y direction, the only two forces acting on it are tension and the force of gravity. So there's no forces in the x, and the y is the force of gravity minus the force of tension equals ma, and you can rewrite that as mg minus ft equals ma.
When thinking about the rotational dynamics equation for this problem, we don't need to worry about force of gravity because that's acting at the pivot point here. So it's not going to have an effect on the torque. We're going to start with this equation. Torque equals inertia times angular acceleration. And we know that the inertia of a circle, which it tells you, solid disk, it tells you it's going to be a solid disk. And we know that the equation for inertia for that is 1/2 mass times radius squared times the angular velocity. Torque is going to be equal to force times the smaller radius. And that's going to be equal to the smaller radius because in torque you're just worrying about the force that the string is acting on this inner circle. And this inner circle has a radius of 0.05, so that's going to be the smaller radius. When you're talking about inertia, you're going to want to use the bigger radius because it's the inertia of the entire object. So you're going to end with an equation of F equals mass times radius squared times the angular velocity over 2r. In order to determine the linear acceleration or any acceleration for this object, you're going to want to combine the two equations that you've already found so that you can have less variables. So you're going to get the equation mg minus mass r squared, angular velocity over 2 smaller radius equals mass times acceleration. The mass will all cancel out because they're all going to be this. So you're now left with g minus r squared acceleration over 2 little r equals a. Although now you're just trying to solve for this a, so you want to get rid of this other variable, which you can do using the equation a equals acceleration times r. We're going to be using the little r in this equation because the force is acting on this smaller circle, so you always use the radius that the force is acting on. So now you can input that equation into here in order to get rid of angular velocity. So it's going to be g minus r squared and a divided by little r over 2 little r equals acceleration. And then you can start inputting your knowns. And then now you can just solve for acceleration, which will be acceleration equals 1.78, and that's meters per second squared.
So in order to find angular acceleration when you have the linear acceleration, you can multiply the angular acceleration by the radius. So it's just 0.78 is the linear or the angular acceleration times the smaller radius, which is 0.05 meters. And when you divide them, you end up with 35.6.
To determine the time it takes for the yo-yo to fall 1 meter, we're going to use linear acceleration. And so first we're going to identify our variables. So the original position of the yo-yo is at 0 meters. Then it falls 1 meter. and its initial velocity is 0 meters per second because it said that it started at rest, and we do not know the final velocity, but we just found the linear acceleration, which was 1.78 meters per second squared, and we want to find the time. So we're going to use the equation x equals x naught plus v naught t plus 1/2 acceleration times time squared, because this equation doesn't include final velocity, which we don't know. So then we plug in our variables so that 1 is equal to 0 plus 0 plus 1/2 times 1.78 times t squared. And then this makes it so that 2 equals 1.78 times time squared. And then we just divide by 1.78 and then take the square root of t to get our final answer of the time to equal 1.06 seconds. Finally, to determine the angular velocity of the cylinder after it's fallen 1 meter, we can use our time from the previous problem, and we can use the angular acceleration, which we also found before. So once again, we're going to identify our variables, and we know that it has an initial angular position of 0 radians, and we do not know the final position, and then it has an initial angular velocity of 0 because it started at rest, and we do not know the final. That's what we're trying to find out in this problem. And then we do know our angular acceleration, which is 35.64, which we found, like I said, in the previous problem. And directly before, we found the time to be 1.06 seconds. So for this one, we're going to use the equation of the final angular velocity is equal to the initial angular velocity plus angular acceleration times time. I'm going to plug in our variables, and that will eventually get us the answer of our final angular velocity to equal 37.78 radians per second.